Hi there, welcome to Chem. I'm Mrs. Newman, and I have another AP Chem multiple choice question dealing with intermolecular forces. The reason being, the College Board quite frequently asks questions about how intermolecular forces affect things like melting point, boiling point, or even vapor pressure. So it's a great topic to have a very sure understanding of. So let's do a little chemistry. The problem begins by stating, consider the molecules represented above and the data in the table below. Another thing you should know about the College Board exam is that they love their pictures, their data tables, even their graphs. So one really good habit to get into is to actually analyzing what they give you in those pictures and data tables. So let's try it out. The very first molecule they give us is what's called nonane. Now, nonane is an organic molecule, meaning it is mainly made up of carbon atoms. In fact, here it's made up of 9 carbon atoms, hence the prefix non. So quite honestly, this molecule is a rather long chain of carbons. Not only that, but the only other atom in this molecule are hydrogen atoms, making this a hydrocarbon. Now, your hydrocarbons like this are very symmetric molecules, which indicates that it's a nonpolar molecule. Now, your nonpolar molecules are going to experience what's known as London dispersion forces. The second molecule they give us here is what's called 2,3,4 trifluoropentane. So now we've got a carbon chain that's made up of just 5 carbons. Not only that, they've switched out some of the hydrogen atoms for fluorine atoms, 3 of them in fact. Now, fluorine is the most electronegative atom in the periodic table, which means it has the greatest ability when it forms bonds with other atoms to actually pull those electrons towards it in those bonds, meaning it's going to always have a slightly partially negative charge to it. That makes this molecule now a polar molecule. Not only that, but because you've got fluorine involved here, there's always the potential for hydrogen bonds as your inters. Except with this particular molecule, since those hydrogens in the molecule aren't directly bonded to those hydrogen atoms aren't directly bonded to a fluorine atom, it doesn't have the ability to form those hydrogen bonds between different molecules. So here it's only going to experience dipole-dipole interactions. As its primary intermolecular force. It could also experience London dispersion forces as a secondary intermolecular force. So those are the molecules we're dealing with. Let's take a look at the data that they give us in the data table. They give us the compound names again. They give us also the molecular formulas of each molecule, and they give us the molar masses. Now take a look. Nonane, even though it has a significantly greater number of carbons or a longer chain, it only has a slightly higher molar mass than the 2,3,4 trifluoropentane. Not only that, but the boiling point, if you notice here, for the nonane is much greater. Which is interesting because usually your London dispersion forces are the weakest type of intermolecular forces. But At your boiling point, what you need to keep in mind is that all of the energy goes into breaking the intermolecular forces so the liquid can enter into the gaseous state. Now, the stronger those intermolecular forces are, the more energy needs to be put in, and the higher or the greater the boiling point is. So this indicates that nonane actually has stronger inters, despite the fact that it's only a nonpolar molecule. So let's take a look exactly what it is they're asking us. They tell us nonane and 2,3,4-trifluoropentane have almost identical molar masses, which is true based on the data, but the nonane has a significantly higher boiling point, also true based on the data. Then they say, which of the following statements best helps explain this observation? So let's take a look at what they give us. Letter A states the CF bond is easier to break than the CH bond. Well, this is just plain crazy talk. Because your CF bond and your CH bond, they're within the molecule. That makes them intramolecular forces. And your intramolecular forces will never break at a melting point or a boiling point. So that doesn't explain this observation whatsoever. Letter B states that the CF bond is more polar than the CH bond. You have to be careful of this. College Board likes putting in true statements as options for an answer, and this is a true statement. But again, it has to do with intras. Intras don't have anything to do with your boiling or your melting point, so also not an option. Letter C says the carbon chains are longer in nonane than they are in 2,3,4-trifluoropentane. Another true statement. Let's talk about it. What you have to remember with your nonpolar molecules is those London dispersion forces are actually what's referred to as induced dipoles, meaning when two of those nonpolar molecules collide, their electron clouds shift, causing a momentary dipole to occur, and then they can be attracted to each other. Well, the larger or the longer the chain of the molecule, the more polarizable they become. In other words, the stronger the intermolecular force becomes. Not only that, but with your long chains, you wind up having a longer surface area. Now, the more polarizable your nonpolar is, the stronger the LDFs they're going to experience. So I like letter C. Letter D states the carbon chains are further apart in a sample of nonane than they are in 2,3,4-trifluoropentane. This may be true, but since they're further apart, then they're actually going to decrease the intermolecular force and weaken it, resulting in a lower boiling point, not higher. I hope this helps you prepare for the May exam. Continue to follow along for more AP Chem content. See you soon.